On this problem, we're going to look at 1999, which is on page 24 of your packet. This is, again, an acid-base equilibrium problem that goes with chapter 16. It's 1999. We have NH3, which is a classic weak base, reacting with water. It says that in the aqueous solution, ammonia reacts as represented above. We have a 0.018 molar NH3 solution at 25 Celsius, and the hydroxide concentration is given to be 5.6 times 10 to the negative 4 molar. In answering the following, we assume that the temperature is constant and volumes are additive. So this is a pretty straightforward problem. We want to begin by writing the equilibrium expression for the reaction. So Kb, because we have ammonia, equals products over reactants is how you set this up. So we are going to have the ammonium ion, NH4, the hydroxide ion, and then on bottom the original NH3. So this is our Kb expression. In the problem, they do not give us the value of the Kb, so that's not something that we can write down. All right, let's move on to part B. Part B says to determine the pH of this solution. If they had given us the value of Kb, we could solve for the pH by setting up a Rice table and then plugging into the K expression, but that's not what we have here. We don't know the Kb value, so we can't use Rice. What we do know, however, is the value of the OH concentration. We know that it is 5.6 times 10 to the negative 4 molar. And so we're just going to use our pH equations to work our way back to the pH. Okay. So the first thing that I'm going to do is remember that hydroxide times hydrogen equals Kw, which is 1 times 10 to the negative 14. So if I plug in what I know, OH is 5.6 times 10 to the negative 4 times the hydrogen concentration equals 1 times 10 to the negative 14. If I solve this by dividing both sides by 5.6 times 10 to the negative 4, I'll get my hydrogen value. And my hydrogen concentration is 1.79 times 10 to the negative 11. So we have our H concentration, 1.79 times 10 to the negative 11. So we are going to negative log that value to get the pH. So negative log of 1.79 times 10 to the negative 11. And that's where we get our answer, 10.7. And our answer does make sense because we're dealing with ammonia, which is a base, so our pH is greater than 7. All right, our next task, part C, is to determine the value of the Kb, the base ionization constant for ammonia. So in order to do this, if we think back to our first, oh, I erased part A. Okay. Did I? Yes. If we think back to our K expression, we had the Kb was the NH4 plus, the OH minus, and the NH3. So in order to solve this, we need to know all of these values at equilibrium, and we don't necessarily know all of that. What we do know is the OH concentration at equilibrium. The problem told us that it was 5.6 times 10 to the negative 4. We know that the NH3 begins, the initial value is 0.018. This, again, the equilibrium value is 5.6 times 10 to the negative 4. So we need to figure out all of the values at equilibrium, and the best way to organize our thoughts on this would be a Rice table. So that's what we're going to set up now. So we have our NH3 plus H2O, double arrow, NH4 plus, and OH minus. The water is not going to come into play because it's a liquid. So the NH3 starts at 0.018, and these of course start at 0. The change is actually something that we do know this time. We're not going to call it X because we again know the equilibrium value of OH over here. We know that it is 5.6 times 10 to the negative 4. Well, since it started at 0 and it's now 5.6 times 10 to the negative 4, the hydroxide change was plus 5.6 times 10 to the negative 4. And that means that it's going to be the same change for the NH4 plus right next to it, plus 5.6 times 10 to the negative 4. So that's its final value, 5.6 times 10 to the negative 4. If we gained on the product side, we lose on the reactant side the same amount because the coefficients are the same. So we simply calculate this initial minus the change. So 0.018 minus 5.6 times 10 to the negative 4. So we know numbers for all the equilibrium concentrations, so we simply plug that into the K expression and we have our answer. So on top it's 5.6 times 10 to the negative 4. There's 2 of them, so that's squared. On bottom we have 0.018 minus 5.6 times 10 to the negative 4. And that's going to give us our answer. I do want to mention that, let's see, this value right here could be omitted because it's a weak base. The loss of original base is insignificant in compared to how much we started with. So you could omit that and I believe you would get the same answer. What we should get for K is 1.8 times 10 to the negative 5th. That's a value that you're going to see very frequently as we encounter a lot of problems with ammonia. That is the KB of ammonia. All right, we have one more part, the percent ionization of the NH3. So remember that percent ionization is the amount that ionized over the original times 100. So on this one, the amount that ionized is the same as the amount of hydroxide that was produced, 5.6 times 10 to the negative 4th, over the original amount, 0.018 times 100. For weak acids and bases, this is usually less than 5%, and on this one, that is also the case. We get that 3.11% of the original ammonia actually ionized or dissociated or reacted with the water, however you want to phrase it. That is how much that actually changed into the products. So that finishes up our problem, 1999 in the acid-base chapter.